I will present our work called Model Inversion Robustness Can Transfer Learning Help at CVPR 2024. In this work, we try to answer a question if transfer learning can help improve MI robustness. My presentation includes 4 parts. First, we present a quick overview of MI. Second, we present our proposed TLDMI, stands for Transfer Learning Based Defense Against Model Inversion. Third, we explore MI robustness via TLDMI. Finally is the conclusion, including main key takeaways from our work. We start with the overview of model inversion. In deep learning, the classifier, or we call target classifier in MI, is normally trained on private dataset. After training, only target classifier is published. A question arises, is there a risk that attackers could exploit access to a trained model to extract confidential information from private training data? The answer is yes, that is model inversion attack. Model inversion attack aim to infer and reconstruct private training data by abusing access to a model. Current state-of-the-art MI attacks form the problem as a GAN latent W search constrained by the attack ID. The W is optimized through gradient descent to maximize the target classifier likelihood. By searching on W instead of searching on image X, the search space is significantly reduced. Therefore, the state-of-the-art MI attacks could lead to 90% attack accuracy. Now we move to the second part, where we introduce our TLDMI, stands for Transfer Learning Based Defense Against Model Inversion. Regarding the research gap, existing MI defense introduced additional regularization into the training objective with the goal of minimizing the dependency between input and output or latent representation. Such regularizations are contrary to the main training objective, result in considerable degradation in model utility. In this work, we take a novel perspective and propose TLDMI to render MI robustness that can minimize the degradation in model utility compared to existing MI defense. Here is an overview of our TLDMI. Normally, training a deep neural network model includes 2 stages, pre-training and fine-tuning. In the pre-training stage, the target classifier is trained on the public pre-trained dataset. Hence, the target classifier is encoded with public pre-trained dataset, denoted as green blocks. We hypothesize that in the fine-tuning stage, if we fine-tune the target classifier with lesser number of parameters, denoted as pink blocks, if it could encode lesser private information in the target classifier. In the remaining of this work, we use theta c to denote number of parameters fine-tuned on the private dataset. Compared to existing MI defense, our TLDMI takes a novel perspective while require the least changes in training or architecture. To validate our hypothesis, we provide a comprehensive study on MI robustness via TLDMI. First, we conduct an analysis of layer importance regarding MI and classification tasks to justify our MI defense. We compute feature information for each layer regarding classification and MI tasks. The results show that first few layers of a target model are important for MI tasks. Meanwhile, these layers do not carry important information for a specific classification task. Therefore, our TLDMI, by limiting the number of layers encoding information from private training dataset, could reduce attack accuracy while minimizing the model utility. Next, we conduct the empirical validation on our hypothesis. As mentioned, theta c indicates the number of parameters fine-tuned on the private datasets. We observe that better MI robustness can be achieved by reducing the number of parameters fine-tuned on private data. Finally, we conduct a comprehensive comparison with existing MI defense. We observe that our TLDMI can improve MI robustness with the least reduction in attack accuracy compared to existing MI defense. Finally, we discuss our conclusion. In this work, we propose a simple and highly effective TLDMI. Our idea is a novel and major departure from existing MI defenses based on the dependency minimization regularization. Then we conduct the first study to analyze layer importance of MI task via feature information. Next, we conduct empirical analysis to validate that lower MI attack accuracy can be achieved by reducing the number of parameters fine-tuned on the private dataset. Finally, we conduct comprehensive experiments to show that our proposed TLDMI achieves state-of-the-art MI robustness. The main key takeaways are the first key takeaway, first few layers of a target model are important for MI task, while the layers do not carry important information for a specific classification task. Second key takeaway, better MI robustness can be achieved by reducing the number of parameters fine-tuned on private training data. Final key takeaway, through extensive evaluation, we demonstrate our approach to prevent encoding of private data information in the first few layers as an effective MI defense. We achieve state-of-the-art MI robustness with the minimal change in training target classifier. Thank you for your listening.